Today we're going to look at disjoint and overlapping events. This is a probability discussion and hopefully a little bit of fun. Let's start with some vocabulary. Disjoint events are events that share no common outcomes, so they're also called mutually exclusive. Overlapping events do share something in common. Now, as a math definition, great, but what does that mean in actual practice? Well, how about you try some? I've given you 5 samples here. You decide if these are disjoint or overlapping. Go ahead and pause while you think. All right, welcome back. Let's see if this is going to be disjoint or overlapping. And it turns out, depends. In the Halloween candy situation, it's considered disjoint if you and your friend had nothing in common. Like if you got all chocolate-based candies and your friend got all things like lollipops and sweet tarts and gummy fish. It would be overlapping if you and your friend, when dumping out your bag, found you had some things in common, like maybe you each have Reese's or something like that. In the favorite foods sample, it'd be disjoint if you are a total carnivore and will only eat meat, but your friend is a complete and strict vegan. There really is no dish that could be made that you two could sit down and eat together. It's overlapping if, say, you'll eat just about anything and your friend is vegetarian. So there are lots of vegetarian-based dishes that you're willing to eat, so there'd be some overlap there. In the movies, it'd be disjoint if you love anything by Disney, but your parents refuse to watch anything by Disney. There is not a single movie that you could put on that you guys could sit and watch together. It's overlapping if, say, you both love the Marvel movies, but maybe you like Frozen and your parents don't. So you wouldn't watch Frozen, but you could pick a Marvel movie and watch them together. With the class schedule, it's disjoint if you and your friends have no classes in common. So you would only see each other like at lunch before or after school. It's overlapping if there are classes you and your friend do have together, like science or fine arts. In the number cube problem, it's disjoint if between the two roles, there's no overlap. So if by the end of the situation, you wanted an even or an odd number to have rolled, those are disjoint because the first roll is even, the second roll is odd. There's not much that you can do there. If in this case you want the first roll to be even, the second roll could be anything 4, 5, or 6, there is some overlap between it. So if it's like by the end of it, if I've gotten an even or a 4, 5, or 6, I win, well, there's a little bit of overlap. If you don't get your even on the first roll, there are, the 3 that you could get on the second roll, but if you did get the even on the first roll, the second roll, the only thing different is the 5. So why does all of this matter? Well, because it affects your chances. So in order to have some fun with this, rather than just make up some boring thing like cards or marbles, I thought we would go to our local carnival and play Pluck a Duck. If you've ever seen Pluck a Duck, it works something like this. There are a bunch of little rubber ducks that are merrily floating along in some kind of little river, or kiddie pool, or something like that. And each of the ducks has something underneath. Let's say that we have 40 rubber ducks and they're numbered 1 through 40 on their little bottoms. And you can't see that because their little bottoms are in the water. Your job is you pay your money, usually like $3 or $5 or something like that, and you pick a duck, you lift it up and you look at its little bottom and see what prize you've won. So at this particular booth, because it's a mathematical pluck a duck, if you pull a prime or an odd number, then too bad, you lose, that's it. Now that means a prime or an odd that doesn't fall into any of the other categories. Now if you pull an even number, then at least you get to draw again. So you haven't lost your money yet, you get another shot. If you pull a number that's less than 10 or is a multiple of 11, you're going to get a small prize. If you pull an odd or a multiple of 3, you get one of their medium prizes. So like a small prize is one of those little tiny stuffed animals. Maybe the medium is like a decent sized stuffed Pokemon. And if you pull a multiple of 13 that's also even, you get the giant prize, the super stuffed thing that people are always walking around on their shoulders because they're like huge. Let's look at the probability of these things happening. So 40 numbered ducks. If your chance of losing was just prime or odd, well, you have two ways to win that, pulling a prime or pulling an odd. So we're going to list those out. Here are all the prime numbers. Here are all the odd numbers. If you pull any of those numbers, you lose. Okay, so are there any numbers that overlap? Well, sure. Pretty much the entire prime list falls on the odd list because, except for one number, primes are all odds. So there are 12 winners on the prime list, and there are 20 winners on the odd list. These are overlapping events. So then, is my chance of losing flat out just 12 and 20, 32 different things out of 40, and so it's 80% chance? Well, that doesn't make sense, does it? It's not like the ducks are labeled prime and odd. They're just labeled with the numbers. So really, how many different losing numbers are there? Well, there are 12 primes and 20 odds, but that prime list is really only contributing one new winner to the pile. So there are the 20 odds plus that one prime number of 2. There are really only 21 losing numbers, which gives you 21 out of 40 or 52.5%. Now, maybe this is the $1 game. If you pay $1, this is the way you can win your prize. Now, let's say that we go to the draw again. Maybe you have to pay $2 to get the right to draw again. So if you pull an even, you get to draw again. And there are 20 evens, so it's a 50-50 shot. Straightforward, right? Now let's look at that small prize. Sometimes you have to pay more to shoot for like the small prizes, but let's say we're looking at just the small prize. The probability of a number less than 10 or a multiple of 11. Now as soon as you see the word or, you have to consider, is it disjoint or overlapping? This is where listing out your options can help. The numbers less than 10, which would win you a small prize, are 1 through 9. The numbers that are a multiple of 11 that would win you a small prize are 11, 22, and 33. So are there any overlapping values between the two ways you could win a small prize? No, they're disjoint. If you're on the number less than 10, you win. There are 9 ways to win that. If you're on the multiple of 11, there are 3 more ways you could win based on that. So there are 12 ducks floating around this pool that would qualify as a small prize winner. So you have a 12 out of 40 or 30% chance of winning. Cool. How about the medium prize? That you get an odd or a multiple of 3. Well, let's take a look at that. I see that word or again, so I have to think, are these disjoint or overlapping events? So here are all my odds, and there are all my multiples of 3. Do you see any repeats? If so, how many? Turns out there are 7 repeats. So there are 20 odd winning ducks. There are 13 ducks that are multiples of 3. If I added those together, I'd be saying I have 33 chances of winning. The thing is, are there really 33 chances of winning? What do you think is the actual number of winning values? Pause for a moment. Figure it out. Did you get 26? Well, of course. That's because there are 20 odds, 13 multiples of 3. That's 33 options. But 7 of them, those red numbers, are being counted twice, once in the odd group and once in the multiple of 3 group. So we have to subtract 7 to just remove the double count. So there are really 26 different ways you could win at this prize, which gives you a 65% chance of winning. Now let's ponder that. You have a better chance of winning the medium prize than you do the small. You have a better chance of winning the medium prize than pulling an even or an odd. We'll come back to that in a bit. Let's just look at the large prize, getting a multiple of 13 and even. Now the word and means it has to qualify as both. It has to be a multiple of 13 and it also has to be even. So my multiples of 13 are 13, 26, and 39. There's only one of them that's even, so there's only one way to win the giant prize. 1 out of 40, 2.5%. Now let's go back to that medium prize being 65%. Why do you think that has the biggest probability? Few things. Let you in on some amusement park game secrets. First of all, the games are not rigged. People say games are rigged, meaning you can't win. They're not rigged. Are they structured in such a way to limit your chance of winning? Absolutely. Could a basketball game have a hoop that's a little bit smaller than standard? Sure. Could you have a ball to throw at a stack of something that maybe doesn't have quite the weight of a softball or a baseball? Maybe. But you still have a chance of winning. And here's the other thing. All of those prizes, like that medium prize, does not cost that amusement park very much to purchase. So if they charge you $3 to play the game and you win the medium prize, you're probably paying $3 to win a prize that costs them less than $1. Which means that every time you pay your $3 and lose, you're funding a prize for later on. So really, the amusement park doesn't lose by giving out these prizes based on what they charge. And if a lot of people are walking away with the medium prize, psychologically, it looks like people win the game, you're more likely to play. There's a lot of psychology that goes into the probability behind gaming. Just saying. Is this too complicated? Maybe. Is it? Let's look at this just with math. Let's sum it all up. Let's go away from the ducks and just get back to the basics. With a disjoint event, because they have nothing in common, you basically get to add up the ways each one can happen and then put it over your total outcomes and you're done. If you're dealing with an overlapping event, that means they do have things in common. So you can add up the ways to get each one, but then you just have to subtract out the number of things they have in common because they would have been counted twice. And then you put that over the total and you're done. Now in formal math, we would say to find the probability of A or B, two different events, if they are disjoint, it's the probability of A plus the probability of B. That's it. If they overlap, it's the probability of A plus the probability of B minus the probability that you would get both, the overlap. So let's try this out and let's switch to a new game, something a little less complicated. We're just going to pull out a deck of playing cards. The jokers are not there, so you have 52 playing cards, numbered from ace up through 10 and then jack, queen, king, 4 different suits. You randomly pull one card out of your shuffled deck. What's the probability that that card will be a face card or a spade card? Now, we're going to do this one logically first. The face cards are king, queen, and jack. Each suit, diamonds, hearts, clubs, and spades, has those 3. So you have 4 suits, each having 3 face cards. There are 12 total face cards in a deck. And they're called face cards because they actually have a picture of a person on them, so you see a face. The spade is one of the suits. There are 4 suits that equally divide up a deck of cards. So there are 13 spades in a deck, 52 cards, 4 suits. Now, is there an overlap? Well, are there face cards in the suit of spades? Yes, there are 3 of those. So then, how many winning cards are there? 12 face cards plus 13 spades minus 3, because I would have double counted my face cards in spades. There are 22 winning cards. So my chance of this happening is 22 out of 52, or about 42.3%. If you are wondering why and how that can be true, if you have a deck of playing cards or can find a virtual deck that you can sort, do it. Flip up the cards one at a time. Every time you get a spade or a face card, put it in one pile. Every time you get something else, put it in the other. Once you've sorted the entire deck, I'm willing to bet you'll have 22 cards in your winning pile. Try it. And now let's look at how formal math would have done the problem. Formal math says These are overlapping because there are face cards in the suit of spades. So I'm going to be using the P of A or B is P of A plus P of B minus P of both. So the probability of face card or spade is the probability of a king, queen, or jack plus the probability of a spade minus the probability of pulling the king, queen, or jack of spades. The probability of a king, queen, or jack is 12 out of 52. The probability of a spade is 13 out of 52. The probability of the king, queen, or jack of spades is 3 out of 52. You'll notice I didn't reduce any of those fractions. I'm going to be adding and subtracting them. I want common denominators, so why get uncommon denominators to then have to get common denominators? So the probability that we're looking for is 12 out of 52 plus 13 out of 52 minus 3 out of 52, which is 22 out of 52, or 11 out of 26, or about 42.3%. So this is all I got for you today in the basics of disjoints and overlapping events. If you feel like you need more, I've got it for you. If you feel like you've gotten all you need for today, all that you can soak in, then go ahead and stop here. I have 3 problems for you to complete and submit. If you feel, though, that you'd like a little more challenge, keep watching. The additional challenge is going to look at probabilities involving diagnostic testing. So it's like having a test for something and how accurately it can predict that test and the probability that an administered test will give a correct diagnosis. Given that we've been through COVID-19, testing for antibodies, testing for being positive for the disease, these are all things we're living with. Maybe it'd be interesting for you to see the math behind knowing how accurate such a diagnostic test could be. If you'd like that challenge, feel free to keep watching. If not, go ahead and stop, and good luck to you with your problems. Okay, so I don't have a whole lot of details quite yet about the COVID-19 testing because it's still coming out. So instead, we'll just use a hypothetical situation so you can see the mathematics. The American Diabetes Association estimates 8.3% of people in the United States have diabetes. If you're not familiar with that disease, diabetes is a disorder of the body that makes your body incapable of regulating its blood glucose, sugar levels, and insulin levels. Insulin is what the body releases to sort of counteract blood sugar. When you have diabetes, your body can't figure that balance out on its own. So it's important to know if you have it. If you have diabetes, there are things you'll need to do: tracking, testing, modifying your diet, perhaps supplementing with things like insulin. And if you don't, you can actually die from this imbalance. If you don't have diabetes, you don't want someone telling you that you do, and now you take on all these restrictions and testing for no reason. So an accurate test would be important. And medical labs are always looking to improve their testing. Of course, the best would be 100% accuracy. So let's say a medical lab has decided to look at a new diabetes screening test, and they've determined it is 98% accurate for people who do have diabetes, and 95% accurate for people who don't. That means that 98% of the time, if someone is diabetic, this test says yes. And that 95% of the time, if someone is not diabetic, this test says no, you are not. Now, the lab gives the new test to a randomly selected person for whom they know nothing. What's the probability that this test will result in an accurate and correct determination? So what are we looking for? In this, we have 2 events we have to consider. First of all, does the person actually have diabetes in the first place? And then, does the test correctly show their status? That's really what we're looking at. So think about this as another 2-way table. Diabetes or no, accurate or no. Now, given all of this, we've got a lot going on here. There's definitely some weirdness. I think a tree diagram is going to be helpful to see what's going on. So here we go. Big old tree. So there's the population from which our random person's going to be drawn. So, reach outside the lab, grab some poor person off the street. When you grab that poor person off the street, the person will either have diabetes or not. If the person has diabetes, when given the test, either the test is correct or not, which would be giving a false negative. If the person doesn't have diabetes, either the test is correct or not, which would be giving a false positive. Now, this might look like, oh, easy. There are two options, and each option has two options. The problem is, my options are not equally likely. Whether a person is diabetic or not for real is not equally likely. And neither are the test results equally likely. So what we have to do now is build in the accuracy. So what is the likelihood that a random person will have diabetes? We know it's 8.3%, or as a decimal, 0.083. Then what's the probability that the person won't have diabetes? Well, that's the complement, which means that's the rest of it. That's the other 91.7% of the population, or 0.917. Now, let's go down the road of a diabetic person. So let's pretend we grabbed a diabetic person in our random grab. We don't know it yet, but we did grab the diabetic person. Now, what's the chance that the test is going to correctly predict that? According to the lab, there's a 98% chance it will give a correct result. That means there's a 2% chance that it's going to be wrong. Now, let's go to the person who didn't have diabetes. Let's say our random person doesn't have it, and we don't know that yet, but doesn't have it. We know that our test will be 95% accurate in saying, yeah, you're diabetes free. We also know it has a 5% failure rate. There's a 5% chance it's going to give the incorrect diagnosis. So this is different than a two-way table. This one is really looking at not equally likely events. So now, we have to get the correct test result. To have the correct diagnosis is one of two events. Someone that's diabetic gets the positive test, or someone that's not diabetic gets the negative test. And what I did is I highlighted those pathways with the two colors, just so you know, if I'm looking for event A, diabetic positive test, I'm following the green pathways. And if I'm looking for event B, no diabetes negative test, I'm following the orange pathways. So let's take a look at the calculations. Event A, probability that someone who is diabetic gets a positive test is going to be the probability that they're diabetic multiplied then by the probability of it producing a positive result if indeed the first happens. So that's the 0.083 times the 0.98, which is 0.08134, or about an 8% chance that a diabetic person will get a positive test. Well, an 8% chance that a random person will be diabetic and have a positive test, put it that way. Event B is that a random person will not be diabetic and get the correct negative test. So the probability of a non-diabetic person was 0.917. The probability that then that person would get a correct test is 0.95. And so there's an 87% chance that if I grab a random human off the street, they will get a correct test result. You might think, yeah, but it was 8%, now 87%, that's not 100. Don't forget, there are those few times when the test will be wrong. Now, if I want the probability of event A or event B, getting the correct diagnosis no matter how it started out, this is disjoint. You can't be both diabetic and not diabetic. So there is going to be no overlap in this group. So that means I have the probability of A, 0.08134, plus the probability of B, 0.87115, which is 0.95249, or roughly this test will accurately give a correct result about 95% of the time. So this gives you that idea of 95.2% of the time, this screening test will accurately predict whether a random person has diabetes. Imagine the implications that has for something like a pandemic. If we had a diagnostic test that could prove with 95% accuracy whether a person has immunity to a particular disease. Is that good enough? What decisions could be made if you had that level of accuracy? So, a lot of really cool things that probability can do in our world that have nothing to do with math class. Hope you enjoyed your extension.